Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today, we're glad to have Demba from MIT, who is going to give a presentation on enhanced MVDR beamforming. This is a joint work with Diné and I during this summer. Without further ado,
Thanks, Chan, for the introduction. Hello, everyone, and thank you for coming. My name is Demba. I'm an intern in the CCS group. I'm here to talk to you of what I've been working on this summer, which is essentially applying MVDR beamforming to speech enhancement using an array of directional microphones. Now, traditional MVDR beamforming assumes that the gain of the microphones is uniform. So an interesting question arises as to when your microphones are actually directional, how do you compensate for the different gains within the framework of MVDR beamforming? So this is one of the questions that we try to answer with this work, and it's done in collaboration of Diné Florencio and Chad Zhang of CCS. So really quickly, let me introduce the beamforming problem. Essentially, you want to estimate some desired signal, for example, me speaking, observed in the presence of noise and interference, the fan, for example. Now, the easiest way you could do that is by having, let's say right now, a close-talking microphone or a microphone further away from me. The problem with that is, yes, you'd be able to reduce a lot of the noise, but because the noise and the speech overlap in time and frequency, the risk is that you would actually distort the signal, although you would be reducing the noise. Now, to add degrees of freedom to your system, why do you not use multiple microphones? And what that does is that it allows you to actually take advantage of the fact that the speaker and the sources of interference are actually located at different spatial locations. And you'd be designing what is essentially known as a spatially selective filter. Now, the goal of this work was twofold. The first one of theoretical interest that I've mentioned in the beginning, which is essentially how do you compensate for mic with different gains within the framework of MVDR. The second one was to propose or design a practical speech enhancement algorithm that is based on this framework. The outline of my talk is as follows. I'll first give a brief overview of beamforming, talking about the simplest solution, which is delay and some beamforming. Another simple solution, which we will refer to in this talk as best mic selection, will be introduced, and that you can sort of think as a form of beamforming, albeit a very simple and naive one. I'll try to make the connection, and I'll then introduce traditional MVDR beamforming. The second part of the talk will focus on how we attempted to compensate for gain differences of the microphone within MVDR. Then I'll go through some details on our implementation, as well as results, and conclude and future work. Now here's the basic problem setup. Actually, this room is the perfect one to introduce such a problem. You have a source of interest, the speaker, that is observed in the presence of noise and interference and recorded at microphones, which in this example could be sitting on top of your head, just like in this room. And you're interested in forming an estimate of the source based on the data recorded at the array. That is essentially what the first two equations are saying, that you're observing a delayed version of the source, as well as the effect of the microphones on the source, which is represented by the alpha 1 through n, and noise, which could be the fan, as well as the reflections of the source, and also the reflections of the noise that are due to the room geometry. Now, the MVDR problem is how, using the signals recorded at each of the microphones, can I somehow compute a linear combination of those signals such that I can obtain an estimate that is good in some sense of the desired signal, the speaker. Now let's look at some of the simplest solution. The first one is known as delay and some beamforming, And essentially what you're doing here is that you're taking advantage of the fact that if you know the location of the speaker, as well as the location of your microphones, you can exactly compensate for the time that it takes the speech to actually reach the microphones. And that is what delay and sum beamforming would do. Compensate for the delay of propagation to the microphones and sum those signal. Mathematically, the weight W, the optimal beamformer weight W in the case of delay and sum is given by the delay vector divided by n, where n is just a normalization factor that ensures that the gain and the direction of the signal of interest is 1. Now, the problem about such a simplistic solution as delay and sum beamforming is that its assumptions on the noise fields are way too simplistic, in the sense that it assumes that the only noise that you're having to combat is independent and identically distributed, what is usually referred to as instrumental noise, just a sensor noise. And it is obvious that in realistic scenarios, that is not the only noise that you're trying to combat. So what I'm trying to say is that noise such as the fan or the reflections on the walls is not specifically modeled or taken into account in a solution such as delay and sum beamforming. Now, one other thing you could do, which is another simple solution, and which somehow takes advantage of the noise field, is that instead of using all of my microphones, why do I not just use the one which has the highest signal-to-noise ratio? Essentially disregarding whatever other recordings I have with the other microphones. Now, the problem with such a solution is that you would think, or at least you would hope, that having n degrees of freedom is actually better than having one at all. And you would hope that you can use those auxiliary microphones to actually cancel the noise and better estimate your signal. So in sort of between these two approaches, a more elaborate solution is what will be the topic of this talk, and it is known as minimum variance distortionless beamforming, that I will introduce in the next slide. So sorry, I do not mean to bore you early in the morning with these equations, but it's just to set up the problem. So what the minimum variance distortionless response beamforming is saying, it's a solution to the above optimization problem. Essentially, the intuition behind this is that you want to minimize the noise variance, the variance of the noise part of your signal estimates, subject to the constraint that in the direction of the signal, in the direction of interest of the speaker, you want the gain in that direction to be 1. So you want the energy of the signal of interest to be preserved. Now, Q here is the covariance matrix of the original noise. Now, so the first part is what deals with the minimum variance part, so W transpose Q W, and the second, the constraint, is the distortionless response one. Now, it has an elegant closed form solution, which is the second equation. And to build some intuition on that second equation, let's just worry about the numerator of that equation, and specifically W transpose. And let's assume that the noise covariance matrix has eigenvalues lambda i's, and that its eigenvectors are the VI's. So intuitively, what MVDR beamforming is saying is that when receiving your signal at the array, you should project that signal on the eigenvectors of your noise covariance matrix and put a higher weighting on those projections that are less correlated with the noise. Essentially, that's how you are able to attain noise cancellation in MVDR beamforming, the minimum variance parts. The distortionless response part is guaranteed by the constraint that you have there, and that is essentially what the denominator of W is. It's the constant that you would get by enforcing the distortionless condition. Now, I've mentioned in the slide earlier that delay and sum beamforming is a simplistic form of beamforming, and it is actually a particular case of MVDR beamforming where the noise covariance matrix is assumed to be identity, essentially that you have uncorrelated noise at the sensors. Now, let's take a quick look at what an example MVDR directivity pattern would look like. And so if this looks messy, it is meant to be messy. What I'm trying to convey here is the fact that your MVDR beamformer is trying to optimize different things at the same time. And in the next slide, I will focus on what is marked as source yarn interference to get some better intuition on what the MVDR beamformer is doing in actuality. So on the left-hand side, so just to tell you what I've done here is that, so what's happening here is that the directivity pattern is the response of your microphone array as a function of the direction of arrival as the source, as well as frequency. So what you will see in the next slide is a cut taken in this picture here along the direction of arrival axis.
What is the geometry of the microphone array simulated here?
So here we simulated a circular one. A circular array.
6 elements?
6 elements, yeah. Yeah. So after taking a cut along the direction of arrival axis, what I'm trying to show here is the fact that as guaranteed by MVDR beamforming, in the direction of the source, which here we simulated to be at 36 degree of azimuth, in the direction of the source, you have a guarantee of a gain of 1, which is what this is showing at all frequencies. Now, in this particular case also, we simulated interference that is located at 68 degrees of azimuth, and it's a fan. Essentially, what you need to know there is that it's a low-pass signal, so that what the MVDR beamforming is that it is trying to cancel the energy of that interference that is mostly concentrated at low frequency. So it's not trying to do much at high frequency, because since it's also trying to cancel other stuff like the reflections, the state of mind of the MVDR beamformer is that I'm going to spend time, or I'm going to spend my degrees of freedom trying to cancel my noise where it has the bulk of its energy. Where it doesn't have a significant portion of energy, I'm not going to worry too much about it. Now, what are some issues with the traditional MVDR beamforming? So the first one and foremost is the fact that a priori, you do not know what the direction of arrival of the source is. You need to rely on some sound source localization step, which obviously due to noise and the like will not be perfect all of the time. We'll have to incur some errors there. Now, one way this can be mitigated is if you not only using audio information to do the sound localization, if you can also add some video information to increase the robustness of the sound source localization step. Now, let me just say that this was not our focus here. Our focus was not to increase the performance of sound source localization. So the focus here was the second point where, if you recall, I defined earlier the array response vector. So it's essentially a vector that says that the source, as recorded by the microphones, is a delayed version as well as scaled by the gain of the microphones. Now, in traditional MVDR, the assumption is that the alpha I's, the gain that is due to the microphones, is uniform, assumed to be 1, essentially. Now, this turns out to be problematic, especially when your sensors are directional, which means that the gain at each sensor is highly dependent on the relative angle between the sensor and the actual source. So in the rest of the treatment, we'll essentially focus on trying to compensate for the dependency of the gain of the microphone on the relative angle between the source and the microphone. So this is just to build some intuition real quick by what I meant earlier, which is that, so on the left-hand side, what I have is a figure of a circular array of microphones with 6 microphones. You have a source that's sitting in front of microphone 1, and we'll assume that's direction theta equal to 0. Now, if you define delta theta I to be the relative angle between the source and each of the microphones, traditional MVDR beamforming will put an equal weighting in the D vector on each microphone, because it inherently assumes that the microphones are directional. Now, what we're saying is that if you assume, this is a contrived example, but if you assume for 1 second that the gain pattern of the microphones is the same and that it is invariant with frequency, again, it is a contrived example, but it is just to build some intuition. So if you assume for a second that the gain pattern of the microphones is independent of frequency and the same for all microphones, what I'm saying here is that mic 1 should get a bigger weighting than all of the other microphones. mic 2 and 6 would get the same weighting, mic 3 and 5 would get the same weighting, and mic 4 would get a different weighting altogether. And let me make this clear here. So this would be what we would consider in this particular case as the wrong array response vector, and the correct one should be the following, assuming again this very simplistic directivity pattern.
Which means you assume a full, just a full cardioid.
I'm sorry?
You assume a cardioid magnitude response.
So not,
In that directivity pattern.
you can say so, but this example was essentially a toy, just a toy example to build some intuition. But yeah, I assume that you mean that you're more used to seeing this in a polar plot form. Yeah, I could have plotted it like that. But yeah, you can assume that. Now, in practice, we're not obviously going to use a very simplified model such as this one to model the directivity of the gain pattern of the microphones. So let's see how we're actually trying to account for the fact that the microphones have different gains based on the data that is received at the array. One point that I forgot to mention here is that, so we only worry about compensating for the gain of the microphones in the array response vector and not in the covariance matrix Q. The reason is that the covariance matrix Q is computed based on data received at the array. So it already contains all information about the directionality of the microphone, about the location of your noise source, and the like. So there's no need to actually attempt and compensate for the directionality, for the different gains of your microphones at the level of the covariance matrix Q. Now, more equations. Let's try to make this painless. So what this is saying is that, so at the array, at each microphone, you receive the source delayed, scaled by the gain of the microphone, as well as some noise. So if you assume that the source and the noise are uncorrelated and compute the energy that is received at microphone I, you get the second equation, which essentially says that it is equal to the energy of the source multiplied by the magnitude squared of the gain plus the energy of the noise. So rearranging that, which is the third line, what you see is that what can actually be computed from the data is the magnitude squared of the gain at a particular microphone times the energy of the source. Well, you don't know what the source is. So the magnitude squared of the gain of the microphone is not observable on its own. From the data, you can only compute the product of the magnitude squared times the energy of the source. Now, let me pause here and say that this is not an issue. Why is it not an issue? So I started off saying that we are interested in actually estimating the magnitude squared of the gain of the microphone. But it turns out that I cannot observe that directly from my data. Now, it's not an issue because you're not actually interested in the magnitude squared gain of the microphone in an absolute sense. You're interested in the magnitude squared gain of the microphone in a relative sense, in the sense that you want to determine how much should I weigh each microphone relative to the other microphones in trying to form my estimate. So what we say here, which is the last equation, is that although I can only observe magnitude of alpha I times magnitude of S, at a particular frequency where I'm doing my beamforming, I'm just going to normalize all of the channels by the maximum across all frequencies. Now, I know this does not make sense yet, but in the next slide I have an illustrative example that can make sense out of this. So coming back to what I was saying, so you have 6 channels, 320 frequency bands, and you compute a beamformer for each of the frequency bands that are relevant to the speech bandwidth. Now, what I was saying earlier is that what you observe is magnitude of alpha I times the magnitude of S. And this is just an example vector. It's just to build some intuition. In this particular case, channel 2 has a higher weighting than all other channels. And since I'm trying to determine what the relative importance of a given microphone is compared to the other microphones, all what I'm going to do is that I'm going to normalize by the maximum over all channels, in this particular case, channel 2, which means that in computing my beamformer, although I do not know what the directional gain of the microphone is I'm going to put a weighting of 1 on channel 1, on channel 2, excuse me, and the weighting that I'm going to put on all of the other channels will be what the original weighting was, normalized by the maximum, which in this case was channel 2.
So these numbers are magnitude or really like magnitude multiplied by something?
No, it's magnitude. Which ones? Which ones?
So then like a 0.64, 1, 0.3, those are your magnitude?
No, those are relative magnitude. It's the relative importance of one microphone as compared to the other microphones.
Yeah, so but you still multiply this, like for each pin, you multiply this by the phase. You still do that, or that's something like that?
By which phase? Which phase are you talking about here?
Later, right? There is like you will have magnitude, you will times E times omega.
Yeah,
Okay. So the G's, all right?
yeah. So the G only takes care of the gain part of the microphone.
All right.
Now you're still compensating for the delay of propagation to the microphones.
Okay. So those numbers are G's.
Yeah, those numbers are the G's here.
Okay.
Does this make sense? Yes.
Can I ask a quick
Yeah,
one?
sure.
I'm not sure how you took out of the equation the acoustic gain between the source and the particular microphone, because those are different for different microphones, right? So isn't there an uncertainty?
So which part? Is it in an earlier slide?
I think so. I may have
Here?
There, yes. Because
Almost incorporate both. The diffusion
oh,
and
basically
the
what
decay.
you want is what you call gain incorporates both, right? No.
Yeah.
Never.
Yeah.
Right.
So what I call the gain is the...
It's not the intrinsic gain of the microphone.
No, it's not.
No.
It's also, I guess it's also compensated for the distance, I guess.
Right, yeah, otherwise you wouldn't be able to figure out. Unless the source were at a reference equidistant or something, and
Yeah.
quite chamber, some weird thing.
Yeah.
Never mind, sorry.
No, that's fine. So this is the block diagram of our implementation. So you have your input coming in. They are processed in frames of a particular length with some overlap. And then they go through a voice activity detector, which essentially determines whether a particular frame is classified as speech or as noise. But we're actually adding a third level here of certain frames that we're not sure whether they're speech or noise. And this will become clear in the next slide, if you'll bear with me 1 second. So if you classify a particular frame of speech, you will perform sound source localization. And given your estimate of the direction of arrival, you will perform this enhanced MVDR beamformer and compute an inverse MCLT to get your estimate of what the desired signal is. Now, if a particular frame is classified as noise, you will update your noise covariance matrix, and you will update the noise covariance matrix and feed that into your beamformer. But update of the noise covariance matrix is frozen when you freeze update of the noise covariance matrix when a particular frame is classified as speech. So you only update the noise covariance matrix when it's classified as a noise. You don't update it when there's a particular frame which you're not really sure whether it is a noise frame or a speech one. Now, on the noise frames and the not sure frames, you will still perform MVDR beamforming, but using the weights of the last speech frame that you met. And the process is the same. Take an inverse MCLT and get your estimate. Now, let me come back to the part where I say that we have a 3-level voice activity detection here. And so the idea is mainly simple if you look at what MVDR is trying to do. And the idea here is that certain frames that you're not sure whether they're speech or noise, if you include those, so if you classify those as noise and include them in the estimation of your noise covariance matrix, what may end up happening is that if that frame actually was a speech frame and it leaked into the estimate of your noise covariance matrix, you may end up canceling the source, while what you're essentially trying to do is estimate the source. Because remember, the noise covariance matrix contains information about the location of your noise sources. So if you include some speech into the estimate of the noise covariance matrix, you're essentially telling your beamformer that, okay, whatever you thought was noise but is actually speech, I want you to cancel that. So in our particular case, this classification rule by which we determine whether a certain frame is classified as not sure is that if we meet a particular frame, we're only going to classify it as a noise frame based on its history. So if the past 5 frames that I've seen, those I've classified as noise, okay, I'm going to go ahead and say that this particular frame, I'm confident that it is a noise frame, and I should include it into my estimate of the covariance matrix. But the main idea to get here is that if by any chance the signal leaks into your covariance matrix, you're in big trouble, because you're telling your beamformer to actually cancel the source while you're trying to enhance it. Now, let me...
Can I ask,
Yes?
Because you mentioned 5 frames, which sound reasonable, but depending on your frame length,
Mm-hmm.
5 frames may not be enough for all the reverberation to go away. So some will not. So you may have some of the reverberation noise into your noise covariance. Do you want the reverberation to be in the noise covariance?
Oh, yes, Yes, I do.
In the very early reverberation, you may not catch it with your 5 frame. Right?
So the frame length we're using here is, so the frames are 640 long with an overlap of 320 samples. So I guess, are you saying that...
I think that there's not a problem, right? Because you won't get a reflection before, you could get a reflection before 5 frames, right? Things like reflection from a table, which come quite close to the original
It's
signal.
in the same frame, 20 milliseconds.
So the frames are 20 milliseconds.
Yeah, approximately.
So you wait 100 milliseconds. So there's reverberation that came before 100, right? So it won't hit. Oh, it's 16 kilohertz sample.
Yeah.
Right? But still 50. You could have reverberation before 50. Right? Again, the table environment echoes from the table and stuff like that.
Actually, only in the first 50 milliseconds you can have something which you can reject with beamforming. After this, it's a stochastic process. The reflection survival rate exceeds
It's already
the
multiple refractions. Okay. But that could potentially be an issue, right? Because as soon as I stop speaking, by the time you wait 5 frames to call the frame noise, some of the reverberation went away. So some of the very short reverberation doesn't go into your noise model, right?
Right, although by the time you, since the reverberation is generally non-stationary, so even if it went into the model, by the time you compensate, it would be gone.
Right. So you probably don't want the too early stuff to go in anyways.
It wouldn't
Right?
be there.
Yeah.
By
You
the time
just
you
move
caught
your
it,
head and it's going from different direction.
So, and that's kind of in practice, you tune this 5 number, right?
Yeah, it's the 5 number was pretty much heuristic.
Well,
Yeah.
actually, the lesson we learned is that you always want to be very conservative when you update the queue, so you have to be very sure it's noise.
Right.
So there's actually other ways to do this noise speech classification. Other thing we try, for example, we in the early source localization, we actually take all the 6 channels, we sum up the energy, and we do speech noise detection tracker. But then we also try to have 6 independent trackers to check each channel, and only when all 6 channels say it's noise, then we do a update. Otherwise, we don't. So it appears that these 2 methods have similar performance. But the rule of thumb is you have to be very conservative. Right.
Yeah, because I mean the most conventional way of actually doing MVDR beamforming is the generalized side lobe canceller, and so it's a typical problem in that implementation, which is that you end up with such scenarios where your signal actually leaks into the noise branch of your estimate, and boom, you've messed up your beamformer. Yeah. Yeah, Mike.
so I was going to wait, but since
No, go ahead.
Since you just mentioned it, that was too late for my question. So could you interpret what you're doing as a side lobe canceller where you're just fixing the fixed beamformer part, where you're fixing the gains of the fixed beamformer part, and then the rest of it is, because, I mean, you're sort of doing some sort of adaptive noise thing,
Yeah.
but you're still putting it in this MVDR framework, which requires matrix inversions and things like that, whereas, I'm wondering if you could take the same thing you're doing, which basically just is fixing the gains on the directional microphones, stick that in the fixed beamformer block, and run the side lobe canceller.
I think you can think about it that way.
The problem is that this is directional mic, so you cannot really fix the gain because when the source.
Well, I mean, or update.
Yeah, I mean, you're updating the gain.
No, but the source can jump from one location to another location in very short periods. So even if you do this update normally, but not very fast. But when you speak really switch, the gain of each mic can switch dramatically because of the directionality of the microphones. So we're trying not to do any this kind of adaptivity.
So when it switches in this case, what happens?
So let's say, I mean, this is like the round table device, right, where each microphone is highly directional. So if, say, somebody at this direction talks and immediately someone else talks in the opposite direction, then the gain of the micro can go from the highest to the lowest, and the other one goes from lowest to highest. And normally, this kind of quick switch cannot be really easily kind of adapted.
Well, you make that switch based on SSL, right?
Yeah, we made that done in SSL.
Right. So,
But you still have the same
so can't you put that same?
No, but each microphone we have assumed they don't have the same gain kind of methods.
I think the answer to your question, Mike, is yes. I mean, because, so the way I think about this implementation in GSC is that, so in GSC you're trying to avoid having to invert a matrix, essentially.
Right.
You're trying to save some computation.
Right.
Right?
Yeah, you're just
We're-
trying to do
yeah.
a strain problem.
Yeah. While here we're doing sample matrix inversion. So I'm going to go real quick over some results of. So we actually ran the algorithms on 10 waveforms that were provided by the roundtable team, and we compared three different algorithms here. The algorithm that selects the best mic, traditional MVDR, meaning not compensating for the gains of the microphones, and the enhanced MVDR, where we're actually attempting to compensate for the gain of the microphones. So what you have in each column is, so A, B, C, and D are essentially what I've named those files that were provided, and what you have on each column is the SNR for each approach, and I have the average down there. So some things to note is that the traditional MVDR does not always do better than even selecting the best microphones. And enhanced MVDR, on the other hand, always does better than choosing the best microphone, although to different extents, but it always does better than choosing the best microphones. And only in one case does it not do, well, it does approximately the same as traditional MVDR, and it's on case E. And so the way I like to think about it is that it is not really a case of interest because you're already at a very high SNR. So if you have a 0.1 or a 0.2 dB, you're essentially not gaining anything by trying to battle on that front. So I'm talking about wave file E, which has a total SNR of 23 dB already, just by doing mic selection. So there's not much you can gain there by doing some fancy. Actually, by doing some fancy stuff there, you're taking the risk that if you mess up any of the steps of your approach, you're going to actually take a bad hit. Yeah.
Yeah, but these numbers, so sorry, quick question. They don't include any noise suppression afterwards, right? It's just the SNR gain from the beam.
This is just the from beamforming, yeah. There's no post-processing or anything, no.
And is it fair to say that by having slightly higher SNR on the output of the beamforming, then you can be a little less aggressive on the noise suppression and then have less overall noise suppression artifacts? Have you actually tried that?
We haven't tried.
We haven't played with the post-processing now.
It's likely should be the case, right? Because if you feed the nonlinear noise suppressor with a better SNR, then it will need to do less clipping, right?
Also, you're saying that by having better SNR at the output of the beamformer, you can be less conservative,
More conservative.
Less aggressive.
less aggressive on your
On the nonlinear noise suppressor.
on your okay.
Concentric one, right?
How the signal to noise ratios are measured here?
So what I do is that each of the waveforms, I label some noise frames by hand, So I'll load them in Adobe Edition. I'll find some noise frames. I'll label them by hand. And I use those bunches of frames to compute the noise energy. And assuming stationary noise and the fact that your signal and your noise are uncorrelated, I can actually compute what the energy of the signal is. And then I take the ratio and 10 log base 10 of that. Yeah. So we're not computing it from, we're not taking a frequency transformation or computing it using a speech noise classifier. We're labeling the frames by hand and using those as estimates of noise energies.
These are collected by runtime, but we don't have options. We don't have clean data.
So this is the, so thanks for everyone who actually went over and did the subjective tests. I mean, so essentially, all of those files that I showed earlier, I put on a folder and asked people in the, because we were short of time, I asked some interns and some people in the CCS group to actually take a test and tell us what they thought of the processed outputs. And so the scale that we are using is on the right side. 5 would be that MVDR is much better. 4 would be that MVDR is slightly better. Same. If people thought that the quality of the files were the same, we would give a score of 3. And 2 would be that MVDR is slightly worse, and 1 is that MVDR is much worse.
And this is compared to what? The best mic?
This is just compared to the best microphone selection. Yeah.
Each of these is like 1 Hz or
It's like
seconds or
it's like no. In our case, it was 50 seconds.
50?
Yeah, 50. Yeah.
Each one.
Yeah. Yeah.
It's quite long.
Yeah. Actually, Leeway suggested that.
I thought it's too long.
Eight?
By the time
By the time you get to the end, you forgot about the first one.
I don't remember the beginning, so then I'll be repeated, basically.
That's a good point. Leeway suggested that we actually make the files shorter because of those reasons. I mean, it's not a very elaborate subjective test, but we just wanted to have something to show because we thought that if you show people SNR, there they go again. But I mean, so this preliminary test, we're doing slightly better. We're hoping that if more people take the test, I'm sorry?
How many subjects do you have?
We just have 6. I mean,
Six.
yeah, it's not.
I'm one of those.
Actually, 3 of those people are sitting here, so it's not a statistically relevant test, essentially. Yeah. So we're hoping we can set this up before I go, so that a more comprehensive test can done, and we can get essentially more significantly, statistically significantly.
No, they are all in different.
No, all are different meetings. All. Everything are different.
But they're all like people from.
Yeah, I don't know why this
So people from
roundtable data they all collect from India.
Yeah, from
Some
India.
of them I think they outsource to India to collect.
Maybe that's I was
Something
guessing
like
maybe
that.
some of the meeting was recorded in India or something.
It's hard to
Because the upper speaker was from India. All the speakers are from India.
Their test team is mostly Indian guys.
I see. Maybe that's why. Maybe.
Oh, is
You
it?
mean, it's physically in the country of India?
Yes, they
Yeah,
actually
all
outsource
different.
to capture the data.
So yeah, we're hoping to get together a more fancy subjective test and get better results. So to summarize, what we've proposed is enhancing MVDR beamforming by further reducing uncertainties in the array manifold by essentially compensating for microphones with different gains. And so results of experiments that were made on real data show that they're still preliminary results, but they show that such an approach seems promising and does better than just selecting the best microphone that's out there. Now, some avenues that we've been exploring and that could be possible future avenues are that actually instead of only trying to compensate for the different gains on the microphones, it would be nice if you could somehow be able to also compensate for the phase shift that is also due to each of the microphones. Now, we have some ideas in place, but this is something that requires a bit more exploration and thinking. Now, Zheng Yu suggested that, because currently we're just estimating those magnitude of the alpha I's from the raw data, and it was suggested that we could actually try to impose some types of smoothness constraints on those magnitude estimate based on the fact that although those magnitude curves are very different from microphone to microphone, they have at least some structure to it. So essentially, how can you make use of that structure in allowing you to make better estimates of the magnitude response? And as far as SSL is concerned and the like, so one thing that may happen in practice is that as you're trying to determine the direction of arrival of your signal, if someone drops a pen or there's paper shuffling, so those type of non-stationary noise sources might be detected by your sound source localizer as actually speakers, which is not the case. So it would be nice to have there some way of distinguishing between true speakers and that type of non-stationary noise sources. I don't know, if you ask me, I don't know yet how this could be done, but it's just an idea out there that it would be nice to have. And with that, I'm concluding my talk. Thanks for attending.